Alright, so what I'm going to do is I'm going to create a video explaining the assignment that I gave you. Some of you have turned it in, and I've looked at it, and most of you have gotten it right, but I just need to clarify a few problems here. So what I'm going to do is I'm going to walk you through every single problem for this assignment, so that way you know how to do it when it comes to our exam this Friday. So this first problem is we're looking at two alleles, big B, little b, that exist for mouse coat color. And the big B is for brown, the little b is for white, and we are supposed to calculate the allele frequencies. Now this one's a pretty easy one. They give you the phenotypes, and you're supposed to figure out the allele frequencies. So for brown, let me get my pen here. For brown, I have 301 out of 500. So they already gave me allele numbers. So 301 divided by 500 should give me around 0.6. So there's the allele frequency for brown. And then for white, I have, what is here? You have to take 500 minus 301, you get 199. Divided by 500, 0.4. So there's the first problem. Okay, the second problem. They give us a little bit more. They give us the genotypes. So I have 290 mice, homozygous big B, 425 hybrid, 270 homozygous little b. Calculate the allele frequencies. So what they do here is they kind of help you break it down, where I have the genotypes. And notice that here I have two big B's. So that's why we have to multiply it by 2, because we're looking for the allele frequencies. But I also have hybrids, which means that I have 425 big B's. So I need to add them together. So I have 1,005 big B's. Same thing with the little b here. I have 2 little b's, so I have to take it times 2. But I also have 425 little b's in the hybrid. Add that up, I get 965. So then I add up my total alleles. My total alleles combined, 1,970. So the allele frequency of big B is 1,005 divided by the total number of alleles, and then the allele frequency for little b, 965 divided by 1,970. So for big B, you should get somewhere around 0.51 and 0.49. So there's problem number 2. In 3, we're looking at centaurs. The allele for curly tails, big T, is incompletely dominant to the allele for straight tails. The hybrid results in wavy tails. So we get a different phenotype here. So I have a population of 1,500 centaurs. 315 are curly tails, 820 have wavy tails, and the remainder have straight tails. So basically what you want to do is you want to kind of break it down like they did in example 2, where I have curly, which is big T, remember? Oh man, that's a bad T. Okay. I have 315. And for wavy, big T, little t, I have 820. And then for straight, which is what I have left over, so this is little t, I have 365. So to find the allele frequencies for big T here, I have 2 big T's here, so 2 times 315. But I also have 820 big T's in my wavy centaurs, so I got to add 820. I get 1,450. If I want to find out my little t, so this is big T. If I want to find my little t, I have 365 centaurs with the straight tail, but there's 2 alleles, so I got to take it times 2. And look at my hybrids. I have 820 little t's So my total for little t is 1,550. So when it's asking me for the total alleles, I need to add this number here with this number. So add that up, I get 3,000. So 3,000 total alleles in this gene pool. And then finding the frequencies is just a matter of taking the number of alleles for your big T divided by the total number of alleles. So 1,450 divided by 3,000, you get 0.48, and this is for big T. And then 1,550 divided by 3,000, 0.52 for my little t. So for big T, it's 0.48, 0.52. There's example 3. All right, looking at the practice problem of the PTC. It says I have 70% of people that can taste the chemical. That's the dominant phenotype, and I have 30% that are non-tasters. That is the recessive type. So let me just write down what we know so far. 70% are big T with a dash. And 30% are little t, little t. So knowing this, if I look at my Punnett square, this 30% is going to go here. This is where little t goes. Here's big T. And I'm just using T. You can use any letter you want. But this is 0.3. So to find out what T equals, and remember T is my Q in this instance, I would take the square root of 0.3. So remember T squared is 0.3, so I'll take the square root of that. T should equal 0.54, which is my Q. So when it's asking, what's the homozygous recessive phenotype? Okay, well, they give that to you. That's given. All right, so that's 30%. That's 0.3. Well, then they're asking, what is just Q? So the square root of 0.3 is 0.54. Then it says, find the dominant allele P. Well, now that I know what my Q is down here, remember, P plus Q equals 1. So if Q is 0.54, what's P got to be? Well, subtract 1 minus 0.54. I get 0.46. So there's my P. And then it says homozygous taste testers. So the square root of P squared is 0.2116, because I took. And then finally, my heterozygous taste testers, I'm going to take 2 times my P, which is 0.46, times my Q, which is 0.54, and I should get a number around 0.49. Okay, moving on to the population's genetics worksheets. Looking at earlobes, they tell me that the frequency of the recessive allele is 0.7. What would the frequencies of the following be, assuming Hardy-Weinberg equilibrium? Yes. So they say the recessive allele is 0.7. So if I were to make a Punnett square, I'm going to use R for this. That means little r, which is my Q in this case, is 0.7. So I think a lot of our confusion is coming from, like, when do I use a Punnett square? When do I add up all the total alleles? So hopefully this is clarifying those questions. So if I have Q, remember P plus Q equals 1. Well, I know what my Q is. That was 0.7. What does P have to be? Well, P's got to equal 0.3. Okay. So here we go. We can answer the first part. Big R is 0.3 and little r is 0.7. But now it's asking what are the frequencies for the genotypes, and that's a matter of just filling in the Punnett square. Okay, so for big R, I'm going to take 0.3 times 0.3. That's going to be 0.09. And for little r, I'm going to take 0.7 times 0.7. And that's going to be 0.49. And then for big R times little r, that should give you, oh, and then take that times 2 is 0.42. Because 0.3 times 0.7 is 0.21. Take that times 2 is 0.42. And it says from question 1, how many people in the population of 7,000, so that's my total number of people, would carry the allele for the free earlobes? Now, free earlobes is, let's see here, is that dominant or recessive? It says attached are recessive, so dominant is the free earlobe. And in order for you to have free earlobes, you can be big R, or big R, little r. So you need to account for both of those. So basically, what you are going to do is I'm just going to change markers here for this. If I take 7,000 times 0.09, because that was my big R, I get 630, and then 7,000 times 0.42, 2,940, and then I basically just have to add those two together, and I should have approximately 3,570 people that would carry the allele for the free earlobed. Okay, moving on to the autosomal gene for eye color in females is 0.4 and little b 0.6, where big B is brown and little b is blue. Assuming Hardy-Weinberg conditions, what would be the frequencies for the following? The genotypes for the population. Okay, so they've given me the allele frequencies. If I make a Punnett square, they're telling me that big B, which remember is P, and little b, which is Q, that they've given that to me. So this is 0.4, and this would be 0.6. And now it's a matter of just going in and filling in my Punnett square. So for big B, that's 0.4 times 0.4, I get 0.16. For big B, little b, take that times 2, 0.48. So if I were to fill this in, 0.16, 24, 0.24, 0.24, 0.36, little b, 0.36. There we go. The genotypes for the 5th generation. Now, it says assuming Hardy-Weinberg conditions. That means that everything's going to be the same. So in the 5th generation, I should still have the same allele frequencies. So that's where they're trying to get at there. So it's the same as the 1st generation. And then the phenotypes of the population, brown and blue. So for brown, remember, I can be big B, or big B, little b. So you just have to add them together. 0.16 plus 0.48, boom. You should get 0.64. And then in order to be blue, you are just 0.36. And if I add those two up, I get 1. Okay, an isolated Pacific Ocean exists in a recessive allele for psychic ability, which enabled the lucky natives to complete witch doctor school. This recessive allele was found in the population of 2,000 natives at the frequency of 10%. And so it's asking how many witch doctors are there on the islands. So for that first one there, let's see, sorry, I lost my spot. 2,000, take that times 0.1, and you get 20. So that means on the island there are 20 witch doctors, because this was the frequency. And they say that the witch doctors as a recessive allele, so little r, or I don't know, whatever letter you want to use. Then it says what proportion of the population would be hybrid. All right, so this is Q. So I know this is 0.1, this is 0.1, well, P plus Q equals 1, so this is 0.1. What does P have to be? 0.9. So if I go in and fill in my Punnett square, 0.01, yes. And if I take 0.9 times 0.1, I get 0.09, 0.09, and then 0.9 times 0.9, 0.81. And so they're asking how many of the population would be hybrids. They are looking at this right here, so you got to add them up, which is basically your 2pq. 2 times your p, which is 0.9, times your 0.1. And that is 0.18. Okay. Or you could say 18%. Looking at lizards. 18 out of 50 had the recessive phenotype for short tails, little t, little t. Okay, so if I write this information down, I got 18 out of 50. That means little t is 0.36. So here's my Punnett square. This is 0.36. So if I take, whoops, not P, I want this to be Q. My bad. Take the square root. Q is 0.6, which is my little t. Cool. So it's asking, what would be the proportion of T alleles in the lizard population? Well, there's your answer right there, 0.6, because that's my Q. What would be the allele frequency for the dominant allele? Well, P plus Q equals 1. So P's got to equal 0.4. What percent of the population would be heterozygous? So for heterozygous, that's that 2pq. So 2 times 0.6 times 0.4, you should get 0.48. Okay, sheep. White wool color is dominant to black wool color if 25% of the sheep in a large population have black wool. Calculate the following. Okay, here we go. So, 25% black wool, that is the recessive. So that means little b is 0.25. And if I were to make my Punnett square, the square root of 0.25 is 0.5. So this is 0.5, this is 0.5. I know that P plus Q equals 1. Well, my Q is 0.5, so that means my P must also be 0.5. So for this first one here, my big B, and I'm just going to use B, 0.5, and my little b is also 0.5, or you could say P equals 0.5 and Q equals 0.5, whatever floats your boat. Okay, looking at B, the expected proportion of homozygous white sheep. Okay, so this is 0.5, this is 0.5. Homozygous white sheep, I'll change my pens here. That is right here. We're looking for this. So 0.5 times 0.5 is 0.25, so 0.25. The expected proportion of hybrid sheeps, well, this is also 0.25, 0.25. Okay, what happened to my marker there? Okay, it's not working. But the oh no. No, what is this black magic? Okay, so I have just lost function. Oh, it's back. That was weird. Hybrid is 2pq, so 25 times, or sorry, 0.25 times 0.25 times 2, woofda, is 0.50. And then finally, the expected number of white sheep in a population of 750. Now, keep in mind, white means you can be big B, or big B, little b. So we have to add, these all up right here. Okay. So I have 750 times, this is 0.75, these three right here. I get 562.5, so you can just say that. You want to round up, that's fine. I'm looking for a ballpark number here. Okay, and then finally moving on to the last one. This one was kind of tricky, I'm not going to lie, but it's the same kind of concepts that we've been dealing with in the previous problems. So we're supposed to determine the allele frequencies for big R and little r, and they give us genotypes. Okay, so first we got to figure out the alleles here. So I have big R is 37. Yes. Big R is 20, and then little r is 7. Okay. So to find my big R allele, well, I'm going to take this 2 times 37. But then I look at my hybrids, I also got 20 big R's there. I'm going to get something like 94. But we're not done yet. Okay. Let's just move on to the little r. 2 times 7. But I also have 20 little r's. And I get 34. Now they want the allele frequencies, so I need to figure out my total number of alleles, which will be 128. And you're probably wondering, okay, how'd you get 128? Well, for the total, it's 94 plus 34. Okay. So 94 divided by 128, I get 0.73, and 34 divided by 128, 0.27. So 0.73, 0.27. And you notice that they equal 1. Now the second part is asking, use the Hardy-Weinberg equation to determine the expected genotypic proportions. So now that I found my P and my Q, or my big R and my little r, this is where I plug it into a Punnett square. Okay. So my big R is 0.73, 0.27, 0.73, oh, okay, 0.27. And I go in and I just fill everything. So 0.73 times 0.73, we get something like 0.53. 0.73 times 0.27, I think I get like 0.2. I better check my math there. Okay, 0.1971, but I'm just going to round it for 0.2 because you'll see why in a second. And then finally, my little r, 0.27 times 0.27, I get 0.07. And when I look at my Punnett square, it equals 1, which is awesome. So now this is, I just have to write these numbers down. So big R was 0.53, big R little r, 0.2 plus 0.2 is 0.4, and then little r is 0.07. Then it says use proportions to determine the expected frequencies in a population of 64. This is where I'm just going to take 64 times the genotypic proportions that you just calculated in part B. So if I were to take 0.53 times 64, I get around 33.94, so I'm just going to round to 34. So this was 64 times 0.53. This will be 64 times 0.4. You should get around, well, we'll just go, I don't know, 25.6. You'll see how it shakes out at the end. And then 64 times little r, 0.07, and I get something like 4.4. Okay, so that's how you do the worksheet. So make sure you just check your worksheet with what I just did. Make sure you understand it because there may be a couple multiple choice questions where you need to answer questions about Hardy-Weinberg. Okay, thank you.